So if you look at the first page of your formula chart, in section 3, where it says sampling distributions and inferential statistics, they really are giving you that very first formula really is for z-scores. It also is for a host of other things, but it's also for z-scores. Because if we look at that, the standardized test statistic, a z-score is a way of standardizing. So z equals, well, what is it that we're standardizing? We're trying to look at the means, right? So we're looking at what we actually got minus the mean over the standard deviation, right? That's a statistic, right? For this one, we have a piece of information, that's a statistic, minus the parameter, that's for the whole group, right? Parameters for a population, divided by the standard error of the statistic. For this, the standard error is the standard deviation. Now, we'll do other standard errors later, but so that really does tell you z-score. Now, I've never thought to use that one because z-score makes so much sense to me. I never look at this for z-score, but it's there if you need it. All right, so let's look at some examples. And I'm going to write some stuff down because there's a lot of questions about this. All right. So life expectancy in the United States varies some from state to state. The lowest life expectancy at birth in 2012 was 73.09 years. And that's in Washington, D.C. The highest was 80.23 years in Hawaii. And then the mean for all states was 77.19 with a standard deviation of 1.57. All right. So let's take a look at this. First of all, let's calculate the z-score for Washington, D.C. So our z-score is going to be what we actually observed in Washington, D.C., 73.09, minus the mean, which is 77.19, divided by the standard deviation of 1.57. Clearly, that's going to be negative. Is it negative like 2.4 something?
Negative 4.1.
Negative 4 point?
Whoa.
Yeah, I was thinking it was about negative 2.5.
For the full answer, my bad.
Yes.
I was just doing 72.
Oh.
I haven't finished it yet.
So this is about negative 2.6? Okay.
Yes. That's exactly it, actually.
So now it asks us to interpret this z-score in context. Okay? Being able to do things in context, super important to us. So, yeah. A z-score of negative 2.6 for the life expectancy in Washington, D.C. tells us that, so what does that z-score tell you? I'm sorry?
It's over 2 standard deviations.
Okay, so it's more than 2 standard deviations below. So that puts it in the bottom, what?
10%. Or
No.
it's 90th percentile. I mean, no, the 10th percentile.
No.
2.5%. Wait, it's not.
Wait,
It's
no.
95% is in the middle.
So 5%.
So, so that means 2.5% is in each tail. But we're only on this one side. So that's the
2.5%.
bottom 2.5%.
Oh, because 95% is between -2 and 2 standard deviations.
Correct. So that leaves 5 for the tails together.
2.5 on each.
So it's
Okay.
2.5 on either side. That's one of the things that's really confusing about that.
That makes a lot of sense now. I get that now.
Tells us that
Washington's life expectancy.
the life expectancy in Washington, D.C. is in the bottom 2.5% of all states in the U.S. Z-scores don't have, Z-scores are unitless.
Ah, okay.
There are no units in them. It's actually probably less than that because if it was just 2%, that's the bottom 2.5. So we would expect it to be in the bottom 2%, which if you think about it for just a moment, there are 50 states. The worst one is going to be the bottom 2%,
Yeah. That makes sense.
right? This tells me that the model is probably pretty good, right? We're applying a standard, a normal model to this without really even knowing, well, is it really normal? Does this, if we were to actually look at a histogram, would it be one where it's unimodal and basically symmetric? Probably. Things like this tend to be that way. If you do anything where it's like you measured the circumference of 500 people's heads, okay, assuming that you picked some sort of random sample, it's going to be basically normally shaped. It's going to be that bell-shaped curve. Okay, most things that occur naturally are that way. Now, can you have some outliers? Sure. You know, if you've got Andre the Giant in there.
You got Hunter.
Pardon?
Hunter, you said the giant.
What did you say?
Did you say Andre the Giant?
Yes,
And you're talking about height?
I'm talking about head circumference.
Oh, well, yeah, if you have Hunter, the football player in our grade.
Oh, you said if you have Hunter.
Yes.
I heard Hunter, but I heard Hunter, and I'm like, what?
Yeah, if you have Hunter, then it's going to skew the data. 'Cause you have
Likely,
Y.
unless you have a big enough sample. If you have a big enough sample, though, you'll probably get someone who has a very small head in that will kind of counteract that. All right. Connecticut has a z-score of 1.09. Interpret this z-score in context. So, a z-score of 1.09, excuse me, for the life expectancy of Connecticut it's like, did I spell it right? Yes. I have trouble spelling Connecticut.
Me too.
Tells us that the model predicts what? So we're a little more than one standard deviation above the mean.
16% around. Right?
What now?
It would be in the top 16%? Because 68?
Well, 68 is the middle,
Mm-hmm.
right? So, let me switch just a second. If the middle is 64,
Mm-hmm.
then that means how much of that is above 50%, approximately?
34.
34%.
Oh, dang it.
So this would be in the 84th percentile. There's 68% in the middle. Split it in half. So there's 34% above 50% and 34% below. So then this would be adding 34 to 50, the 84th percentile.
But that, is that one standard deviation, the 84? Would that be the one standard deviation?
Yes,
But it's 1.09,
I was trying to
right?
do it
Oh, so
like
it's
we
a
did
little
the
bit above.
last one.
right. I'm sorry.
I'm sorry, Mr. Davis.
I was trying
No.
to do it like we did the last one.
We're doing it exactly like we did the last one.
What?
So, okay. So there's 68% in the middle, right?
Yeah. So I thought
That leaves how much?
32.
So that means 17% in each tail, right?
30. Yeah, 32. So it'd be
68, 32.
32. Then it would be 16% in each tail.
Hang on a second. 68. Hang on. 68, 32. 16% in each tail, yes?
They're in the top 16%.
Correct.
Oh.
Which is the 84th percentile,
Oh, I just wasn't following that.
right?
So you have to put 84th percentile. You can't say top.
You could say that it's in the top 16%.
Okay.
Either would be okay. It's like, man,
Sometimes.
It
it's
wasn't
hard to be a
clicking.
woman.
It wasn't clicking.
No, I
Yeah.
understand.
Dun, 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 dun. That Connecticut, or just they, are in the, we'll do it your way, top 16% of life expectancies.
It's like percentile confuses me because it's you're better than 84% of the people.
Right.
But I think of it as like you're in.
You think in yeah, as an overachiever, that would be what you would do.
The top 16%.
Yeah. You personally tend to be an overachiever.
Oh,
Therefore,
thanks.
you think in terms of, I want to be in the top X percent. I mean, would you say that's fair?
It makes more sense, yes.
All right, so let's calculate the life expectancy at birth for Connecticut. Well, we know their z-score is 1.09. We don't know what their life expectancy is. We'll call that x minus the mean is 77.19 divided by 1.57. So we'd multiply both sides by 1.57.
1.71113.
And then we're going to add 77.19 to that.
78.9.
Pardon?
78.9.
78.9? So that's their life expectancy. You know there's a back to this, right?
Oh, well.
Are we out of time?
Oh,
Yeah,
yeah,
it's
it's
about-
about 45 seconds.
Okay. We'll do the rest of it tomorrow where we get into not just where you live matters, but your race matters as well.